Karla Saur. I'm a research scientist at Intel Labs, and today I'm going to talk to you about migrating the next generation mobile core toward 5G with Kubernetes. And this is joint work with my coworker, Sai Krishna Idubuganti. Real quick, I'm required to give this legal disclaimer saying that the stuff I'm going to present today is an open source prototype, not meant for production, so you can't sue us. All right, so first I'm going to start with some background about what I mean when I say the mobile network core, and a little bit about the cell phone networks that I'm going to be talking about today. And then I'm going to talk about what we needed to do to make it even feasible to continue moving this telco workload to containers and to Kubernetes, especially in terms of the network requirements and the performance requirements. And then after I talk about that, I'm going to go into what we did with Kubernetes in order to handle a completely managed, orchestrated solution. So first, when you think about cell phone networks, or when you hear the cell phone network, you probably think about your cell phone that you use all the time. You might think about some of the connected devices that use the mobile network. Some of the Internet of Things use this mobile network to connect to the Internet. And then you probably think about the cell phone towers. That's another very visible component of a cell phone network. All these towers everywhere. As we move to 5G, there's going to be even more towers. And then you know that somewhere in between, a bunch of stuff happens, and all the packets, when you're browsing your phone, make it back to the Internet. But there's a lot that goes on in between the tower and in between the Internet. When I tried to put all of the components of the mobile core network on the slide, it was a complete disaster. There's 20 or 30 different components, and it was very busy. So just to keep things very simple, I'm going to talk to you about two of the main components that are important, at least for our work. First is the MME, that's the Mobility Management Entity, and this handles the main signaling. So when you turn your phone on and try and spin up some data, it needs to create a session in the mobile network. So the Mobility Management Entity says create session, and then if you move around from there on, say I move from the area of one tower to another, you're going to have another modification of that. So the MME handles the signaling part. And then at the bottom, there's this thing labeled SPGW, that's Serving and Packet Data Network Gateway. And this handles a lot of, well, it receives the session information from the MME, but it also handles the main data plane throughput, so the connecting the cell phone towers on through to the Internet. That's all kind of how the network exists today. There's going to be a lot of changes, particularly to the control plane as we move to 5G, but there's going to be a lot of growth. It's going to be growing very rapidly, especially as these small devices in our homes come online. The Internet of Things is going to grow rapidly. It's going to create a large amount of additional signaling traffic, the rough estimates around 100x growth. And then data throughput as well is going to increase as the bandwidth in 5G grows. So we need to take all this into consideration when moving forward with the new network. So traditionally, the mobile core of the network was done on proprietary hardware with closed source proprietary software. This was very crufty and hard to quickly replace and quickly innovate on. And as we move toward 5G, the network core, by the core, I mean the computing in between the towers and the Internet, the stuff, the actual IP traffic flowing through. This core is going to be increasingly based on something called NFV. Have any of you heard of NFV, Network Function Virtualization? OK, so about a third. Cool. So from 3GPP, this is the wireless standards body, from 3GPP, bringing NFV to 5G is going to have a lot of benefits. And when I look at the list of benefits that are explicitly stated, a lot of them remind me of also bringing your application to cloud native. So enhancing the level of automation, having a lot faster service rollout, faster updates, much better networks for making much better metrics to make for better performance and optimization in the network. And so as we move from hardware toward the softwareization with NFV, it's going to be a great benefit to mobile networks in general. To get started in experimenting with this new network paradigm, some of my colleagues created this thing called NGIC. That's the Next Generation Infrastructure Core. And this is a open source reference implementation. It's hosted at OpenCord, which is under the Open Networking Foundation. And this is a software reference implementation of an evolved packet core. So on the left, you see the picture that I showed you earlier, where we have the traditional network with the MME and the gateway. And then as we move toward the right, with NGIC, one of the main differences is that there's this separation of control plane and data plane. There's this paradigm called CUPS, control user plane separation, especially relevant as in the 5G spec. And so that means that all of the signaling traffic is going to be processed in our control plane network function. And then all of the data plane, the actual user data, is going to be processed in our data plane network function. So once we had our control plane and data plane set up as our network functions, we needed to think more about the long-term vision, and we wanted to foster rapid innovation in our research prototype. So we released this code. It's under the Open Networking Foundation, and we're hoping that that will help people innovate on some of the new ideas moving forward. The things that we're focusing on are programmability, orchestratability, and scalability, which to me just screams Kubernetes. So that kind of put the idea in our head toward this avenue of research. And the use of merchant silicon, no more proprietary hardware, and open source software for a much more open network overall. Another thing we kept hearing from everyone we talked to was one of the needs in the new network is scale, scale, scale. So we want to be able to scale in step with traffic. So if everyone is watching World Cup all at once and there's this huge burst of traffic, then we need to be able to quickly spin up a bunch of instances while everyone's watching the games, and then when the game is over, we need to be able to scale down very quickly to save on CapEx and OpEx as much as possible for the telco, from the telco perspective. And when I say scale, what I'm talking to you about today is more replicas of NGIC components. I am from Intel, so yes, scaling in terms of more cores, more hardware, more whatever is important, but today we're talking about scaling out. Our original prototype used just a straight up binary that we ran on bare metal. This was a hassle for dependency management. And then we moved sort of toward VMs. A lot of the telco space today operates on VMs, and so, but there's, as you all know, you need the entire operating system, a lot of extra hassle there, and that really puts a damper on scaling nimbly. So we moved to containers, which solved both of our problems. Everything is contained, and we don't need the extra operating system. But one of the important things that we still had to focus on was performance. So we got a lot of pushback from a lot of people being concerned, are you going to be able to get the same performance that we currently have if we move to containers? What's that going to look like? So before we could get started, jumping right into Kubernetes, we had to do some enablement and testing to make sure that our network requirements could be met for our telco workload, and make sure that the performance was at least close to what we were already getting on bare metal. Here's a little bit of a deeper dive into our network functions, the control plane and data plane. The network names that you see here that start with an S are part of the standard from the 3GPP. So S11 in the control plane is the signaling, session creation, and management. The CPDP interface is our custom network that we use to communicate the control plane, pushing down the new flows, the new session information to the data plane. The data plane is really an interesting creature because it has a lot of requirements and it requires very fast performance. So the SGI interface is unencapsulated user data as we go to the internet. And here we do basically L2 routing. So that a lot of the spoof checking will break things because the IP address doesn't line up with what is expected. So that's definitely an interesting problem that we had to handle with the unencapsulated user data. And then on the other side, we have IP and UDP encapsulation. But really what we very much need is speed. And all the telcos, all they want to hear about is how fast can you move the data through this pipeline. And as we thought about moving to Kubernetes from this networking requirements standpoint, we had a couple of roadblocks that we had to first handle. So first, we containerized the control plane and data plane. So each of these two little blue boxes inside the big blue box of our network functions, each is going to be a pod. And the goal was to be able to scale them separately. So if it's an Internet of Things workload, we'll need more control planes. If we have a very heavy active data user, we'll need a lot more data planes. But how do we maintain the network requirement? The data plane has these 2 or 3 very different types of networks, and it has the need for high throughput. In a lot of telco workloads today, they use something called the DPDK. That's the Data Plane Development Kit. Has anyone heard of that before? All right, at least a fifth. That's good. So this is an open source code that allows you to develop very fast data plane applications. The biggest problem, as some of you may know, right now the Kubernetes networking model limits 1 IP address or 1 interface per pod. So already our data plane pod is in some sort of trouble. What we looked at, what we had to do from there, was we looked at CNI plugins. So this is a container network interface. This is under the CNCF umbrella. And these plugins allow you to describe how to interact with container networking, or in our specific case, how to interact with the Kubernetes networking in general, for our case. And the way this works is, I'll go through a more in-depth example in a second, but generally on pod bring up, kubelet calls out to the CNI registered node, and it sets up the networking, and from there it can launch a whole bunch of more plugins. There's a whole bunch of CNI plugins available. You've probably heard about a few of them at some of the talks earlier today. But there's very basic ones for very simple software networking. There's a loopback plugin, a bridge plugin. From Intel, there's a couple of plugins that we used for our setup. First is the SRIOV plugin. It allows us to create virtual network functions and also allows us to use the data plane development kit for our user space drivers that gives us the really fast performance that we need. But critical to our setup is this Multis plugin. Multis allows you to have multiple network interfaces within your pod. And so Multis is actually acting as a proxy to set up these extra networks. If you're interested in these a bit more, there's several white papers out there on this, or you can just search for a GitHub Multis plugin or GitHub SRIOV plugin. All the code is out there, open source, and pretty well documented. On the left, just going into a little bit more detail, we have the logical setup of the way this networking works. So Kubernetes calls into the CNI plugin, and then first thing that the CNI plugin does is called the Multis CNI plugin. And then from there, Multis is going to be able to call all of the additional networks that you might need. So Multis might set up Flannel or Calico, for example, for your just regular overlay software networking. And this is ETH0. So from Kubernetes standpoint, whatever is instantiated first, and this ETH0 is going to be the network interface that Kubernetes still knows about. So in terms of all of the discovery mechanisms that Kubernetes provides, ETH0 is all it's aware of. And then Multis is able to also create these additional networks, loading the additional plugins, so our DPDK-based SRIOV plugins. On the left, you can see what that looks like in the actual manifestation. We have our pod here, and the ETH0 on the far right going out to Kubernetes standard networking, and then our additional virtual functions with the high throughput. All right, so that was the baseline that we needed to even continue from this point. This is what our actual diagram looks like for our specific pods. We have our control plane pod. We were able to put the S11 network and the CPDP network on one, so we're just using standard networking here. We can use the standard discovery and go through the Calico plugin. And then for our data plane, we have the additional virtual functions set up with DPDK and the user space drivers. And this is the whole diagram is for a single node. We have one CP per pod and one DP per pod, and we'll have multiple copies of those. So I mentioned that Kubernetes is aware of ETH0 in terms of service discovery purposes, but it's not aware of these additional networks that are created by Multis. So that means you're kind of on your own in terms of service discovery based on these additional networks. And so we came up with a very quick, simple solution to quickly do service discovery on other networks. We used Council, we used it as a key value store. So as each new CP or DP instance comes up, it puts it's newly, the CNI plugin will assign the address to the unknown interfaces, and it will put this information in console so that the other pods can discover it. So for example, the control plane might need to talk to a specific interface on the data plane, and that way they're able to query each other, and it fills in the gap of the missing service discovery that we created by the extra network. And so that kind of wraps up the networking parts, but we still had some performance parts that were completely crucial for performance of the data plane. One of the things that was missing was core pinning and isolation. When we started working on this about 8 months ago, there was some third-party, some work from Intel and some work from the community about getting core pinning working within Kubernetes. At this point, as of I think 1.9, the core manager is now beta in Kubernetes. So when you're making your pod YAML file, there's this resource limit definition that you can specify, and you just say, I need this many CPUs. I need them to be guaranteed, meaning I need them to be isolated just for me. And so getting a core assigned is as simple as saying how many you need and whether you need them to be isolated, and Kubernetes takes care of the rest of that for you. This is just my demonstration showing, if you don't know what core pinning is, here's the all of the apps are using all of the cores, and then on the right, app A has been pinned and isolated to cores 0 and 1, so it has those all to itself, which guarantees a certain amount of performance. And the other thing that we needed to do was huge pages. So with huge pages, you can set these up so that you'll have like a 1 gigabyte giant block of memory. This works great for making sure that everything is already available in the cache. If you have a hash table and you're looking up a whole bunch of network flows, if you miss one of the lookups and have to do a fetch, there's going to be a pretty big performance hit. And so in terms of maintaining the same performance we had with the data plane, we needed to have huge pages. Kubernetes provides this as a native resource at beta as well as of, I think, 1.8. And all you have to do in your pod YAML file is specify the number of huge pages that you want to use under your resources. Here's some preliminary performance metrics. So the first line is our performance for native. This means bare metal. We ran our data plane. We pumped a whole bunch of cell phone network traffic through the data plane to see what performance we got. And it was about 1.5 million packets per second or so with all of our performance optimizations turned on. And in the second line, you see Kubernetes with all of our performance optimizations. And it's very similar. The margin of error here is about 50K packets. So it's really within around 5% of the same amount of performance. The last 3 lines show us the amount of impact you have on not having these performance metrics. For example, if we don't have the user space drivers, this is the SRIOV plugin with the DPDK user space driver. Our packets per second tanks to about half. And with core pinning, we're fine. It's about very similar to the prior until we add a lot of noise. So we took we put a while one loop on all of the 88 cores on the machines that we were running this on to simulate a very busy workload. Depending on what other workloads you have running on the machine, core pinning can be very critical. Similarly with huge pages, so there's a little bit of a performance hit there just due to the missed lookups and fetch. All right, now the fun part. We had proven to our management that it's looking good. This is a close enough performance, and we got the OK to go ahead and move forward with this, taking our newly optimized pod toward a fully managed Kubernetes solution. Our application was fairly complicated in terms of the data plane. We had a lot of additional parameters that we would need for each instance, and so actually deploying it was quite a hassle for one instance. The thought of deploying it for tens or dozens or hundreds of instances would be completely unmanageable, so we definitely needed a way to do zero-touch configuration. We also needed to think about lifecycle management, how this is going to be easier for the operator. And then my favorite part is automated scaling. So as traffic grows, how do we scale on demand? So this is what our command line looked like for our data plane before Kubernetes. We had to figure out each of the arguments manually specific to each machine. So we'd have to do lscpu to get the core masks available on all of the machines that we were using on our entire rack, figure out what core mask to pin them on and pass that as an argument. We needed to figure out how much memory was available and manually kind of provision how much memory each data plane instance should get for a specific machine. And we needed to manually create all of the network IP addresses and the MAC addresses. All of this is handled now completely by our Kubernetes setup and the CNI plugins. So the core manager will make sure that none of the cores overlap. It just passes it through a little bit of our scripts. It passes it automatically. And we can launch multiple instances without thinking about any of the things that used to take us a very long time to set up. Also, we wrote a custom operator for NGIC. We use the Red Hat CoreOS operator framework. And an operator is basically a CRD, a custom resource definition, plus our custom controller, which we wrote in Go. And all the user has to do is provide some top-level attributes of NGIC in a YAML file. I'll show you an example in a minute of exactly what the operator needs to specify. But then from there, the operator orchestrates launching of all the components. So we have our CP and DPs set up as Kubernetes stateful sets. We have a load balancer that handles making sure the traffic is distributed. And then it also creates a bunch of additional configuration that we need. The operator creates all the config maps and sets up all of the services that we need. Also, we scale automatically based on some custom metrics that we defined. I'm going to walk through an animated example. So here, company A provides a YAML file. Some of the very rough details is that they need to specify where their MME is located, since we're only providing the gateways. Give some numbers for the subnet mask, and then a little bit of information about there's a couple of smaller or additional settings for custom configurations. But there's only about 12 lines or so that an operator needs to configure, whereas before it was a very, very lengthy hardware-dependent setup. Once the YAML file is sent to the operator spins up a bunch of instances. We start with the operator can specify how many they want to begin with and how they want to scale. And also we support multiple companies. So company B can also launch their similar setup within the same Kubernetes cluster. I'm going to show you roughly how the scaling works. So the orange lines show on startup. The operator creates the load balancer, and then either like 1 or 2 control plane and data plane to get started. For now, I should mention we're scaling in lockstep from control plane to data plane. So for every new control plane, we create a new data plane. Some of our ongoing work is being able to create an arbitrary number of, like an n by n numbers of control plane to data plane. And after it's created those, there's some quick configuration bootstrapping that I talked about briefly earlier. The CP and DP are assigned this network information. They store that in console. The load balancer can retrieve that from console, and that way the load balancer is aware of how many CP instances it has. And all of this is monitored and facilitated by the operator. When it comes to actually running the traffic, so the cloud there, so the traffic is coming in from the MME, and this hits the load balancer. And since we only have 1 instance right now of CP and DP, it's going to go to that instance. Another thing that we do to facilitate scaling is we're using Prometheus, which is, I think Sandeep mentioned that earlier in his talk today. We're using Prometheus as it's kind of a time series database to keep track of stuff as it scales. Keep track of stuff for scaling over time. So the custom metrics we're using are the number of active sessions, and then the amount of load on a particular active session. So if one user is running around all over the place, that active session is obviously going to be a little bit more taxing on the system than a user that is just standing still, stationary. And the operator is continually querying the Prometheus database to check to see when it's time to scale up. When we've hit a specific threshold, the operator triggers a scaling event, and it launches a certain number of additional replicas of the control plane and the data plane. So I mentioned load balancer. We have a telco workload, and all of this, this S11 traffic you see is this encapsulated, telco signaling tunneled protocol. So this is all tunneled traffic. So we looked at a bunch of different existing load balancers, all the popular ones, maglev, etc. But since our workload is a bit different, an L4 and L7 load balancer wouldn't work without a lot of additional work. So at least for now, we wrote our own very, very simple load balancer based on this thing called TIDE. It's a tunnel endpoint identifier. It's a field in the S11 traffic that identifies uniquely which session goes where. We wanted to keep this as minimal as possible. It was just a few hundred lines of Go code, and currently we're using one replica of the load balancer, but obviously we don't want a single point of failure. So when it comes to making this more of a product, we'll have a much more distributed solution. I'll walk you through an example, so it hopefully makes more sense. So the TIDE is a 32-bit number, and that's basically, you can use that to identify which specific session belongs to which user. And we have this very simple table. The only thing stored in the load balancer is this table, so you'll just have one entry for each of the CPs. When a new session comes in, so when you turn your cell phone on for the first time or reconnect to the tower for the first time, the TIDE is going to be 0. So that signals to the load balancer to call whatever magic function that will randomly select or round robin or based on some other metric, select a control plane instance of its choosing. And each of these CPs are provisioned with a range of TIDEs from the operator. So they're non-overlapping ranges. So for example, CP0 has the 1000 to 1FFF TIDE and so forth. So when CP1 receives this create session from the load balancer, it will respond back with a TIDE in its range. Ideally, it would respond to the MME directly, but for now we're going back through the load balancer for some additional tracking. And now for subsequent sessions, all of the subsequent sessions will be tagged with this TIDE, and so the load balancer will know what CP to direct this to. So this allows very fast lookup, very minimal state. It's basically, we just look at the offset of the TIDE and then kind of route from there. All right, scaling. So this is, the dotted line here shows us pumping traffic at a constant rate in our network simulator. And we set a specific threshold for where we want a scale up event to trigger. So at around 6,000 packets or so, this threshold is reached. And there's the blue line there, the second CP instance spins up. We have a whole bunch of health checks. We're using a lot of the built-in Kubernetes health checks to make sure everything is OK in terms of our CP and DP communication and a bunch of stuff there. So there's a bit of a extra, we want at all costs to not drop any packets. So we make extra care. Our spin-up time's a bit longer just to do all of the extra checking. But then from there, the CP1 starts handling the new traffic. And then again, at around 130 seconds or so, the next CP starts spinning up. So I have about 5 minutes. The code for the NGIC gateways, the CP and DP code, is available now. It's hosted by OpenCord under the ONF. The orchestrator code, so that's the custom Go controller and the load balancer, is going to be hopefully posted by the end of the summer. Other than that, anything else, any of the additional stuff I talked about today should probably already be available online. And with that, are there any questions? Particularly any questions related to the performance optimizations. I know that might be more broadly applicable to some of your use cases. All right.
Okay, thank you. Tell me, please, is it some kind of production setup or is just test demo?
Yeah, right now, everything is in a test setup. We have a couple of, there's a few offshoots of this. There's some trials going on right now with the VM-based solution. We're hoping to integrate our Kubernetes-based solution into a couple of more public trials later this year. So this is all pretty preliminary work, but yes.
So you hope to put it into production, not just make some tests and games and fun.
Well, so the way this works is there's this thing called MCORD. It's Mobile Central Office Re-architected as a Data Center. It's this consortium under the Open Network Foundation, and they are trying to create a reference prototype. A lot of the United States telco are part of this consortium. We have regular meetings with the telco providers, and some of in Asia and Europe as well. And from there, hopefully we can work through a similar open standard body like that to, so currently our prototype code is not production ready, but we're hoping to transition that and help transition this open reference implementation to more of a production workload. There's a lot of conversations right now with several different telcos, but yes, that's the current status.
Okay, thanks.
Thank you. In the back?
So I have a question to the load balancing method. Now it's very static. You know that each instance can handle around 6,000 sessions, and you do it based on this. Is this right?
Yes. So the prototype can handle a lot more than 6,000 sessions. We just picked a very very low threshold to make sure that just for demonstration purposes. Our goal is to incorporate a bunch of additional metrics, maybe with Prometheus, in terms of like CPU load and other load there, a bunch of the common hardware metrics in combination with the telco specific. We want to make sure to scale up conservatively so that there's enough buffer in case there's a burst of traffic. So there's going to be a lot of fine tuning there. But yes.
Okay, thank
Thanks.
you.
So my question is, I heard you use several interfaces in one container.
Yes.
I'm wondering, why would you need this? Do you do network routing inside of containers, or what do you use this for?
Yes. That is a great question. It is, so because we are actually, unlike a regular web service where you're maybe serving a user request, we're actually processing the traffic. And since we have very different types of traffic, we have the unencapsulated user data, which is like L2 traffic, so the raw traffic data, and then we also have encapsulated traffic. We have thought, and we are still considering, trying to rewrite the data plane as like a series of maybe microservices and make sure that there's only one network interface. It seems like there's something that we could definitely do there to simplify the networking. But in terms of conforming to the standard, since we have these standard interfaces specified, and in terms of fitting this in to make existing telcos happy, we wanted to make sure to at least first pursue this solution. But yes, that is probably the number one question we get asked is, why on earth is your networking so complicated?
So will you contribute the support of several network interfaces to the Kubernetes community?
Right now the Maltus, the CNI plugin, that's all, Maltus and such are all available already, open source. I think Kubernetes is, I've been sitting in on a few of the SIG networking groups. My understanding is they're pretty set on the single interface. But with the CNI plugins, you have a lot of flexibility to do whatever you need to get done.
Thanks.
Wait, one more over there. And then I think I'm about out of time.
A quick question. The extension of the network interfaces might be useful for other use cases besides the telco stuff too. Would you see it fit for that?
Yes, definitely. So the plugin is very, this Maltus plugin is very flexible in terms of you can launch, once you've launched your Maltus plugin, you can spin up a bunch of additional network interfaces with whatever plugin you want. So you can have, I don't know, I can't think of a specific use case now, but if you wanted 3 different all software like Calico networks, you could definitely do that. So it's meant to be as flexible as possible.
Thanks.
And again, that's all on GitHub. So, all right, I think I'm out of time. So I'll be here. I will be around afterwards. And thank you very much. You've been great.